Okay, hi everyone. I wanted to take a little bit of time and go over some of the basics of photosynthesis one more time, just to make sure you all are prepared. Um, I'm going to start by reminding you that in your book, chapter 6, sections 1 to 3 and 6.9 as well are going to be really useful for reviewing some of this material. But let's talk about photosynthesis. Photosynthesis. Take a moment and think about how you would define this term. It's a process that converts light energy to chemical energy through the synthesis of carbohydrates from carbon dioxide. Okay, so recall that this process takes place inside the chloroplast, which is a double membrane bound organelle inside each cell of a green plant. And you should also remember that there are two main phases to this process. There are the light reactions, or the light-dependent reactions, as we've called them a few times. And then there's the light-independent reactions, which I've been calling the Calvin cycle. But you can think of them as light-dependent and light-independent. Recall some of the inputs, right? You should know the main inputs to photosynthesis. And you should also know the main outputs. What are those main inputs? This one's easy, right? This one's light. But which ones are these? The light-dependent reactions rely on water, and the light-independent reactions rely on carbon dioxide. So the light-dependent reactions. These are all about capturing light energy exciting electrons, and synthesizing ATP and NADPH. These are your energy-carrying molecules. In the process of using electrons to reduce NADP plus to NADPH, those electrons have to be replaced. And so that comes from the oxidation of water. And when you oxidize water, you get oxygen gas and you get some protons. Those protons are used in creating an electrochemical gradient that's used to synthesize ATP. So we've got the synthesis of these energy-carrying molecules. The next part, part 2 of photosynthesis, is the light-independent reactions, or the Calvin cycle. The first phase in a C3 plant is carbon fixation, carbon capture. So we mean pretty much the same thing here when we talk about carbon capture and carbon fixation. This process involves an organic molecule that's in the stroma of the chloroplast. It's in the chloroplast. This is a 5-carbon molecule. And carbon dioxide, which obviously is a 1-carbon molecule, there's 1 carbon in carbon dioxide. And the reaction proceeds to for the synthesis of 2 molecules of 3-PGA. So this is an organic molecule. It's got 3 carbons each. So 2 of those, 3 carbons each, gives you a total of 6 carbons. So that matches up, right? Now, in order to get this reaction to proceed, we need an enzyme. This is the enzyme Rubisco. The C in Rubisco stands for carboxylase. That means it's an enzyme that can fix carbon dioxide, basically. Now, that's the first step. It's just the carbon capture. The second step in the process is called reduction. And in this process, all we're doing is we're using energy in the form of ATP to reduce 3 PGA molecules to these G3P molecules. So each one of these is a 3-carbon molecule. Each one of these is a 3-carbon molecule. So all we're doing is reducing or adding some of that energy. This G3P can be used to synthesize sugars. If a sugar, like glucose, is a 6-carbon molecule, how many G3Ps do we need for that? We need 2, right? So we can keep track of our carbons in this way. But one of the things we need to do with the Calvin cycle, or one of the things that happens over the course of the Calvin cycle, is this RUBP here that's involved in that initial carbon capture needs to be regenerated. So that's the third step, regeneration. How many carbon dioxide molecules are necessary to create 1 molecule of glucose? If you said 6, you're on the right track. It takes 6 of these carbons to make the 6 carbons that are in glucose. Well, how many RUBP molecules would we need to fix 6 molecules of carbon dioxide? You're right, we would need 6. How many carbons are there total if we're using 6 RUBPs? 6 times 5 is 30. 6 times 1 is 6. So how many of these 3 PGA molecules are we making in the end here? 30 plus 6 is 36. Each 3 PGA molecule has 3 carbons. So how many 3 PGA molecules do we get to make? 12. These 12 3 PGA molecules become reduced to make 12 G3P molecules. If you spend 2 of those on glucose, you have 10 remaining. How many RUBP molecules can you make from 10 G3P molecules? Recall the number of carbons per RUBP. You get 6 back, which is exactly the number that you need to start the whole process. So all we're doing with this is adding energy through the process of reduction to make glucose out of carbon dioxide. But we have to go through all these reactions in order to ensure that there is enough RUBP at the end so that Rubisco can do its job. That's how photosynthesis works in a typical C3 plant. The problem is that Rubisco is kind of sloppy. What's the O stand for in Rubisco? It's an oxygenase. So let's look at what happens if we've got Rubisco and we've got RUBP and O2. Let's count our carbons. We got 5 carbons from the RUBP and we've got 0 from here. So we get 1 molecule of 3 PGA and we get 1 molecule of 2 PG. You can't make glucose out of 5 carbons. It's a 6-carbon molecule. The problem here, this is what's called photorespiration, because in order to recover from this, these 2 PG molecules need to be involved in the regeneration of RUBP. It takes 3 of these 2 PG molecules to make an RUBP, and you have a carbon left over. So this is the problem with photorespiration. In order to recover enough RUBP to make this reaction proceed, CO2 is lost and energy is spent. So it's called photorespiration because CO2 is released, which is similar to cellular respiration. But remember, the energy for all of this regeneration phase is coming from the light reactions. So it's called photorespiration. So how do you avoid this sloppy fixation of oxygen by Rubisco? how do you make it so that Rubisco can only ever fix carbon dioxide and you avoid this whole situation? Well, what C4 plants do is they just take Rubisco out of the initial carbon capture. They use a different enzyme called PEP carboxylase that fixes carbon dioxide to this organic molecule called PEP. And the output of that reaction is a 4-carbon molecule called malate. This is why it's called C4. Because you've got this 4-carbon molecule called malate. This happens in the leaf mesophyll. Then they have a specialized set of cells in the leaf surrounding the veins that we call the bundle sheath cells. And malate is transported into those bundle sheath cells. The bundle sheath cells are an area where carbon is concentrated. Because this malate can be decarboxylated in there by a malate enzyme, breaking apart the malate, re-releasing the CO2 so that Rubisco can fix the CO2 in what's effectively a low oxygen, high carbon dioxide microenvironment inside the cell, inside the bundle sheath cell. So C4s, they have the characteristic anatomy that we call the Kranz anatomy. Which refers in part to the bundle sheath cells. This whole process requires energy. It requires extra energy on top of the energy that C3 plants are already spending on the Calvin cycle and maintaining normal cellular processes. But the benefit is that photosynthesis can proceed when carbon dioxide concentrations inside the leaf, so internal, are low, or when the plant is water stressed and has to close its stomata. So under certain conditions, these plants continue to grow, continue to be productive, whereas a normal C3 plant would have to close its stomata and shut down the photosynthetic process to avoid photorespiration. This also confers a higher water use efficiency for C4 plants. Again, because if this is your leaf, here's your little stomata, maybe they're closed now. CO2 inside the leaf is going down. Here's our bundle sheath cells. These are the only cells that have Rubisco fixing carbon dioxide. Normally in a C3 plant, this scenario would lead to photorespiration in a C3 plant. Whereas in a C4 plant, Pep-C comes to the rescue and saves the day and allows the plant to continue being productive, even in a low carbon environment, by fixing carbon dioxide in the normal leaf mesophyll cells. All right, so I hope that helps. Don't forget to look back in your book, section 6.1 to 6.3, and especially 6.9 for understanding C4 photosynthesis. And you can also watch the original lecture video still as well on YouTube.